17. And also from 2015 to 17, for all these years, I had the pleasure to advise him together with Professor Cassie Alberton. I don't know if she is here. In an undergraduate research project about identifiability. Yeah, during that period, Lucas has received 2 Best Paper awards at the WFRJ and presents his work in the international conference that is unusual for undergraduate students. I have invited Cassie to introduce Lucas, but when I asked her, she was very busy with her 2 little kids on these tough days. It's not easy to deal with that. Maurice knows this very well. And okay.
Yes, I do.
So Lucas has defended his master thesis exactly 1 year ago in August, end of August. And the subject was about what he is talking today. Almost, I think, it was the same title. And he was co-advised by Mauricio and me. So now he is doing his PhD with Professor Sigurd Skogestad. I don't know if he has another co-advisor. Work on real-time optimization, machine learning, I guess. So please, Lucas, the floor is all yours. You can comment some about this also.
Okay, let's go by parts. First, I thank you guys for the invitation. It's a pleasure to be presenting to in my home. Thank you guys for being here and watching this presentation. Also, it means a lot to me. This work was produced during my master year. I got a little bit emotional now because these 2 professors that supervise me. Thank you so much for the compliments, and especially Admiro, since he's been my supervisor for a very long time. I miss you guys very much. So yes, I'm just going to the presentation, but and actually, Dinesh is my co-supervisor in the PhD. Well, emotions aside.
Excuse me, I'd like to tell you that at the moment that Admiro cited Professor Skogestad, he entered into the room, you see, into the presentation. So he is also attending. So you have 3 supervisors, 4 supervisors present.
4 supervisors.
Yes.
Oh, Well, so I'm going to begin the presentation about entitled Health-Aware Control and Model-Based Prognostics, Concepts and Application on a Subsea Oil and Gas Separation System. I'm going to try and focus a little bit more on the fundamentals on this presentation, because during my dissertation, of course, you have to present all your results, all the methodology, and etc. So I hope I can take this time to make it a little bit more didactic, especially because I'm focusing also on the master and PhD students who are not familiar with the topic. So I'm going to begin introducing the problem, and then talk about what I did during my master's work, which was comprised of modeling and stationary simulation of the system I was interested. It's identification and control, the degradation modeling and lifetime prediction, and finally the health-aware control implementation and the main conclusions of my work. So when it is said health-aware control, and we are concerned about health of the equipment, we are basically interested in planning when to perform maintenance of the equipment you have in your system. So there are some ways you can do it. I mean, one is, of course, run to failure maintenance, in which You just run your system until you fail, until you get a failure. And then with this, you get major financial losses, mostly related to inoperant time. You can also try and perform preventive maintenance. This is usually based on historical data, in which you try and have some means of telling when the equipment is going to break based on other equipment that have broken before. But the idea would be that you perform condition-based maintenance, in which you try and monitor the equipment condition to define if the maintenance is necessary. But when you do condition assessment, you have to try and use some model to predict what is going to be the equipment condition in the future. And for this, we give the name of prognostics. This approach is also called predictive maintenance. So with prognostics, the ultimate goal is to try and estimate the equipment remaining useful lifetime. And there's a number of ways of doing that. But what we have to keep in mind is that the system is subject to a lot of uncertainty. So usually the remaining useful lifetime, or RUL, is going to be best represented as a probability distribution. So you have to keep that in mind. When you aim to perform the modeling of the degradation process, we have some approaches in the literature. Most of the approaches that are used are based on the statistical models. Some are based on artificial intelligence models. A few of them are based on physics and hybrid models. And why is that? Well, let's take, for instance, the Paris law. The Paris law is a classical attempt of phenomenological or first principle prediction of the crack propagation in systems subject to stress. So we have this power law model in which A is the crack length, and you have a dependence with the stress applied to the component or the equipment. And there's also this very classical study that describes or measures the behavior of this derivative in wear systems. And what is seen is that there's considerable variability, even in highly controlled environments. So you see the process is basically statistical by nature. So it's very natural to treat this with statistical models like linear processes, gamma processes. And when you don't do that, you have to use some kind of statistical methods to account for the uncertainty and the probability. One of these statistical methods is the Bayesian filtering. So I'm going to present some Bayesian filtering concepts. This is well known in the control community. It's kind of Bayesian filtering, but the essence of it is to try and estimate states, hidden states of dynamic systems subject to model and measurement uncertainties. So for you to make the Bayesian filtering treatment, you have to have a dynamic model, which will give you the temporal update of your distributions, and recursive estimation for you to update information with the measurement. And for that, you use Bayes' theorem. We are going to go through a little bit of that. The basic assumption of Bayesian filtering is that the process behaves as a Markov process. So this means that the process is memoryless. The evolution and the observation depend only on the current state. So what has happened in the past doesn't influence anymore, given the current state. So the nomenclature that I'm going to use is this pi for the PDF. So you see an a priori PDF, which is the distribution given measurements up until the previous time instant, and a posteriori when you have incorporated the current measurement. Measurements are given by y. So the first part of the Bayesian filtering is the temporal update, when you have a PDF that is projected in time. This generates the so-called a priori estimate. So you project the previous a posteriori into the current a priori, and you do this by the second integral. And you see that this first term on the integral is the probability of the next state given the current one. And this is called the Markov transition kernel in the Bayesian filtering traditional literature, but it's essentially our dynamic model. So for example, we have this very traditional linear model that represents one Markov transition kernel that is going to be Gaussian. Also, the second part of the Bayesian filtering framework is the measurement update, in which you have an a priori PDF that is updated with measurement information, originating an a posteriori estimate. So you have the incorporation of information into the PDF, and this is done by Bayes' theorem. It's the second equation, and the term in the denominator, it's kind of awkward to look into, but it's basically a normalization, so we shouldn't look too much into it. But what's important is the likelihood function that I have highlighted here. And it's a probability of the measurement given the states. And this is basically your observation model, how you translate the measurement into information about the state. And also, this can be very complicated, but can also be very simple. For instance, a linear model. And when everything is linear in this framework, we can reduce the Bayesian filtering problem into the Kalman filter. So we have assumed linear dynamic model and Gaussian uncorrelated noise processes. And this generates Gaussian distributions throughout all the states. So it's defined by its mean and covariance. And also what is nice about the Kalman filter is that all those calculations involving the distributions now can be only represented by mean and covariance, and these can be calculated by matricial operations, as in those equations in the right, for temporal update and measurement update. But the Kalman filter relies on very strong assumptions regarding both the process model and the distribution of the random variables. So we have some natural extensions for the Kalman filter. For instance, the extended Kalman filter, which is based on local linearization of the dynamic model. So it's adequate for mildly nonlinear systems with Gaussian distributed random variables. So we are more flexible now with relation to the linearity of the model. With the unscented Kalman filter, we try also to do a higher order approximation for the estimate and covariance of the states, which is based on sampling. The sampling is the unscented transformation, which is deterministic and is optimal in some ways. So it's adequate for trying to approximate nonlinear systems and distributions that are non-Gaussian, and which can become non-Gaussian by this nonlinear transformation. The particle filter, for instance, is the more complex of these approaches, which is based on Monte Carlo sampling. And we try to approximate the Bayesian filtering problem and reconstructing the distribution itself. So it can deal with nonlinearities and non-Gaussian random variables. So some important remarks about the particle filter. The strategy that it implements, it's based on importance sampling, which is basically the sampling of particles using trial distributions to try and make the state transition calculations more accurate, only looking into what is relevant. And the use of this approach leads us to the simplest particle filter, the cis filter. Cis filters are very known for having weight degeneracy, which consists of basically you not being able to characterize properly your distribution because you have the curse of dimensionality, and some particles simply are not relevant anymore because of low transition probabilities altogether. So what is best is that if you could return the particles into a more relevant set. And for this, we have resampling. So the SEER filter comes to try and tackle this issue. And then you obtain a set of particles with equal weights and that represent your distribution better. So you replicate important particles and remove low irrelevant ones, let's put it that way. Okay, so that was it for Bayesian filtering. But let's go back to our health-aware control definition. Those are basically strategies that consider prognostics into the control structure, and you try to make your control and operational decisions also based on equipment degradation. The first known appearance of this term in my literature review was by Escobar, in which it was a very simple approach, actually. It was based on a prognostics module and a PID controller, so not necessarily you have to have advanced control structures for you to do health-aware control. But before that, this Pereira, this group led by Pereira, implemented a MPC controller with health constraints. So this term health-aware control is new, but the approach is not that new. So it's hard to track where it began. But in his approach, the failure was prevented on the considered operational window. So we have some other approaches that came after that. Sanchez made an MPC with damage term added to the controller objective function, and he observed the trade-off between process performance and the equipment damage. There are also approaches that model the degradation process as a Markov decision process, and this leads to the reinforcement learning framework. Verheijlen, which is actually watching this presentation, applied scenario-based control to explicitly consider variable uncertainties and considering health as constraints. There's also approaches in which you do hierarchized control to deal with lifetime extension, in which you have an optimization layer and to deal with the economic and health objectives, and an MPC layer to deal with dynamics and control objectives. So as for our case study, it was a subsea CO2 separation system. And this process is important in terms of study of reliability and health, because it's a subsea process. And with subsea process, you aim to minimize process intervention at all costs. So you don't want your process to be running to failure in this case. And it's important that CO2 separation is performed at subsea environments, because fields with high CO2 content are very common. CO2 reinjection extends the oil production, but also when CO2 is removed in a subsea environment, you can reduce the topside equipment load, let's put it that way. You are not so heavily, because the topside environment is very intensive on space. So you want to avoid putting big equipments at any cost. And when you remove the CO2 in the subsea environment, you can reinject readily. So it's very important that we study how to operate optimally this kind of system. So the objectives of this work were to investigate the main aspects of the development of a health-aware control system applied to this process of national importance. So for this, we need to study the modeling of the CO2 separation system, perform identification and control to the process. We also need to study the degradation model, in which, in our case, we focus on the multi-phase pump, because that's the equipment that is most prone to degradation. And we want this model to be sensitive to operating conditions so that we can optimize the system. We aim to design also a prognostics tool, which predicts the RUL of equipment based on this degradation model. And we aimed also to integrate all of this into a unified framework. So I'm just checking the time. Okay. About the system modeling, this is a diagram of the system. It comprises of the reservoir in the lower left corner. So we have a stream coming from it, and that is passed through a valve. This stream is heated by a hot stream from another part of the process, and this heat integration is performed, and then we lead this stream into a flash vessel in which we separate the liquid phases. We have more than one liquid phase into the bottom, and for the top, this current is we have a heat exchanger, we have a pump, and this pump is the one that is prone to degradation. And we have outlet stream that is hot because of the compression. This is the current that is used in heat integration. And the compressed stream is led into reinjection. And the bottom of the flash drum is led into the top side. Okay, so we have valve models. This is basically a model of constant enthalpy, but we also have to model the flow through this valve proportional to the square root of the pressure variation. We have the heat exchanger model, which comprises of energy balances. They were performed in a discretized fashion. So we have a model for each pseudo stage. We have the flash drum model, which is a three-phase flash. So we need to have the mass balances, the energy balances, and the closure equations that describe the conservation of internal energy and volume. It's a flash calculated at U and V. But also we have the thermodynamic model that is the key to this problem. We have the pump model that performs energy balance and also the relation between the pump power and the flow through this pump. So to integrate all of these models, we use the We use Python to model this, to perform the simulation of the system. We use the CO2 therm package that was developed by Souza, which was interfaced to Python. The stationary simulation was performed using fsolve from the SciPy library. So for the stationary simulation, there were some numerical challenges for that. So we had to split the problem into two. We had to solve first the mass balances that involve some of the temperatures of the process and the valve openings. And then we go and solve the remaining equations. The values that I present here are the values for design of the system. So yeah, we performed the stationary simulations, and these are the results. They are described into my dissertation. So after that, it was time for designing the controller to the system. So we have to consider the system in its dynamic form. And the modeling that we performed resulted into a differential algebraic equation system that was challenging to solve, but fortunately, Python has a nice library to solve GAEs, which is the IDA algorithm included on the Simulo package. So if anyone is interested on this kind of problem, this is a nice tool. So possible disturbances are the reservoir conditions and the battery limit pressure values, the pressure on the top side and the pressure of injection. So for manipulated variables, we have basically the valve openings and the duties of the heat exchangers and the pump power, of course. And we selected some output variables that are important for operational purposes, which are the flow from the reservoir, the pressure and temperature from the of operation of flash, the temperature after the heat exchanger, the flows of each of the batteries, the composition of CO2 that is separated, and the liquid volumetric fraction of flash that is important. It's basically a level control. So as this pair volumetric fraction and bottom valve is available for use to stabilize the plant, because we have an integrating behavior on the flash drum. We chose this pair for stabilizing the system. So we tuned the PI controller for that using the SIMC rules. For that, we have to identify an approximate model. And this was done with some step changes into the valve opening. So this is the implementation that we did for the PI model. So it's an idealized version, continuous version. And the new input vector, of course, we have to remove this valve. And now we have available for us to manipulate the set point of this controller. So these are the identification results. So the system behaves almost as a integrating system. I'm sorry. So for that, we use SIMC rules. And for the tuning that we used, these are the servo test and the regulatory test. After that, considering the stable plant, we performed model identification, now aiming to implement the MPC controller. And for the MPC controller, we have to have a good internal model. So we have to make step changes into all of the possible manipulated variables, excluding, of course, the set point of the drum level. So we try to identify continuous time transfer functions. And the number of poles and zeros was defined by inspection of each of the profiles, because the behavior of the system changes between pairs of inputs, outputs. But using these transfer functions that were identified, we aim to describe the system into this linear time invariant discrete time model. So for that, first we converted the transfer functions into continuous time models using some algebraic manipulations, and we discretize the system to obtain this kind of model. Okay, so in here we can see some results of the model identification. This gives us a little insight of the nonlinearity of the system, because we see some variation of gain when we do a positive step change into one of the manipulated variables, comparing with a negative step change. So this happens with most of the variables. Thus, it's important for us to do the positive and negative and obtain an average transfer function, so we don't have too many errors. Some of the variables presented instant response. For instance, when we consider this input-output pair, which is the flow that passes through the same valve that is opened. So it's going to present an instant response. So we have those complexities in our model. Then we proceeded to do a Kalman filter implementation with the equations that I have already shown, but just once again, the temporal update, in which we obtain a priori estimates for the state and covariances, and also the measurement updates, in which we obtain a posteriori estimates. The tuning of the filter is done by changing the Q and R matrices, which are basically the representative of how much you trust your model and the measurement that you have, respectively. And after that, we proceeded to the MPC implementation, which is based on the classical optimization problem of minimizing the deviation of the output variable from its set point, from its desired set point. And this is weighted by Q in this equation, but also we have to consider weights on the manipulated variable, so we don't have a very aggressive response. And this is weighted by S. This optimization problem is subject to some uncertainties, mostly regarding to maximum and minimum values of manipulated variables and manipulation effort, delta U, and also, of course, the dynamic model that we have. And in this dynamic equation, you can see that we have this WK term. This is the Kalman filter state bias, and this is important to correct the internal model of MPC. So it's important that we implement the Kalman filter state bias into the MPC. And this was a very valuable lesson that I learned from this work. So this is the base case, considering all of the what was discussed before and using these tuning parameters for the controller. And which we see that we have no offset, we have the attainment of a new steady state. This was basically a change of set point into the flash pressure, which we can see on the lower left corner of the screen. So now I would like to do some discussion on the importance of the elements of this control framework. The first is the filtering, the most basic filtering, in which we only trust in the internal model and we have no feedback, basically. So the process has some offset because the internal model is not accurate enough, because the system is nonlinear. So we are trying to represent with a linear model. But also when you apply the filter, but when you don't perform model update, you only perform state update in the Kalman filtering loop, we see that there is some offset in the controlled variables. And this is because the model is not being corrected, only the current state. And when you try to do a prediction, the steady state that is predicted, it's not the actual steady state. So the control system is trying to optimize an objective function that is not representative of your process. So it's important to implement the WK term that we see here. We have also done implementation of constraints, and the implementation of these constraints change the steady state that is attained. And this is because we have more manipulated variables than controlled variables. In this case, we have attained a new steady state, and the steady state has not any offset, despite the fact that it's a different position of the manipulated variables. But if we implement other kinds of constraints, the system might not be able to track the set point correctly. Okay, now we come to the degradation modeling part and lifetime prediction. For the degradation model, we hypothesize that the degradation could be modeled by Paris law, which is first principle based, but we consider a random growth rate given by a gamma distribution. And this gamma distribution is very common in the degradation literature. So this model has both the simplicity and variability that is necessary for a degradation model, but also is very descriptive of most systems. So we have this power law model of the evolution, and the delta F variable is distributed according to a gamma distribution. And these parameters are characteristic of the degradation process. And the observation model, we consider it to be comprised of the state and some Gaussian noise. So for this degradation model, we have, I forgot to mention actually that this delta F parameter depends on the pump power. So we can actually manipulate how the system degrades. And here we can see two profiles of the simulation, the degradation model, one with constant pump power and the other one with varying pump power. And we see a lot of curves in the top graphs because the system is stochastic. So we have done several simulations of the same system just for you to have a notion of how is the variability of the degradation process. And this is kind of the expected behavior. So for the correct length estimation, we use the model that we described with this set of parameters that are that try to describe generic degradation process. But what is important here is that we use particle filter to perform state estimation, and then with the state estimation, we try to predict the lifetime of the system. So we use an algorithm written by Speak and Brink, and we adapted it to consider deterministic equations with random parameters, which is this kind of model that we described, as opposed to the most traditional description by probability distributions, as in those Markov transitional kernels and likelihood functions. This is the most traditional. So in here we compare the cis and SEER filters. And the cis filter is given by these simulations. And I try to represent the distributions using size of the dots. So in here, we can see in blue the state estimates, in which we see that one particle is very big while the others are very small. This is very characteristic of weight degeneracy. So this filter was not well suited for my application. But when we implemented the filter with resampling, we can see that we have a lot more uniform distributions in the a priori estimates and in the a posteriori estimates. We also focus that on a posteriori estimates, we narrow down the distribution a lot. So we only consider the particles that are very close to the true state. And for lifetime estimation, RUL estimation, we compare both the cis and SEER distributions. And we see that the resampling strategy is very well suited for this kind of problem, because we see that the distribution for RUL is narrowed down as time passes, where in cis, we cannot do this kind of thing, because the particles that are not important are kept there. So resampling is very nice for this kind of problem. Also, when we consider varying pump power, so we have some model mismatch, but we see here that as time passes and as we incorporate and as we are more and more close to the breakdown of the equipment, we see that the estimates for the distribution get better and better. So this is an example of how feedback or measurement update is important in this kind of problem. As for the health-aware control implementation, we tried to implement a controller that had both the RUL extension objective, but also the control objectives, the set point attainment and manipulation effort terms. But in this case, yeah, we have different time scales. So the degradation is happening a lot slower than the control. So we considered that only the ending value of the pump power is relevant in the degradation. And yeah, this kind of function is not so convenient, because RUL is a random variable. So we have to remove the randomness to treat this problem as deterministic if we want to treat it this way. So we do that by sampling some probabilities before the optimization, and this is related to the probability of each realization. So we transform basically the random variable into a deterministic variable, but that's also representative. Okay, so in the previous, in the objective function, we see that the control objectives and the RUL extension objectives are weighted out by this WHAC parameter. So we see the effect of this parameter. In this simulation, it's with the value of 5, and we can see that set point is attained with some small offset, but also we can see that in the lower right corner that the pump power is minimized, so we minimize the stress in the degrading equipment, while also maximizing the valve opening at the top that is modulating this pump. So when we increase this parameter, we tend to increase this offset, but also as we see here, if it is large enough, we can have divergence of the system, and we are close to the shutdown of the pump, as we can see in the lower right graph. So this kind of objective function is dangerous to work with, basically. We have to pay very close attention to the tuning. We also evaluate the sampling noise. And yes, this was done by fixating the tuning parameter, but also varying the number of particles and how you treat the optimization problem. And we see here that the results are very random, because when you solve that optimization problem, if you have a random variable, that is updated into each of the optimization problems. So if you want that to be not this kind of noisy response, you have to fix those quantiles that I have mentioned that are related to the probability of each of the realizations of the degradation process. This was a comparison of operation of MPC and the health-aware control. And we see here that when we operate using the health-aware controller, we can extend the predicted lifetime of the process by approximately 0.4 years. So this is a nice result, but this approach had a lot of challenges. So let's conclude the presentation. In this work, we have done modeling, we have done control and prognostics. So yeah, looking back, it was a lot to do in 1 year, but it was well worth it, because I have got to learn this different approaches. The control strategy was successful, and we show here the importance of model correction based on Bayesian filtering when you have model plant mismatch, which is basically every time. And we propose a degradation model that reproduces the expected behavior for degradation. And a particle filter was implemented for state estimation and RUL prediction successfully. In the health-aware control part, which was the last results that we got, we contraposed health and control objectives. So it's not optimal to treat those problems in the same control layer. So, but also one could try and use multi-objective optimization to optimize both objectives separately at the same optimization problem. We saw unstable behavior with high weight on the RUL extension, and this is a known issue in the development of economic MPC, for instance. And as I said, it's hard to treat those problems in the same layer. So for future work, it's probably nice to treat this problem in a hierarchized control framework, in which you do lifetime extension in some management time window. And then if you do it on this slower time scale, you have time to treat the the probability distributions in a better way, because then you would have more computational power in your side. This work was also published at Processes. So if you're interested in seeing more about this work, this is the title of the paper, Integration of Prognostics and Control of an Oil CO2 Subsea Separation System. And yes, that was it. I hope you enjoyed it, and thanks for the attention of everyone.
Thank you very much, Lucas, and for your very nice presentation. You have presented so many interesting topics. As you consider the process, this concept of health-aware control is, as you said, is a new concept, and so people may be very interested. Also, the process is also very interesting. We have some people here from Petrobras, for example, and we have proposed a model and a simulation for this process that was proposed by Petrobras. And also you treated the question of the degradation model. So you have very interesting aspects to discuss. So the discussion is now open. I ask, please, if you could use the chat, it would be easier to organize. So I ask you, please, to make questions and comments using the chat. Okay? They are very welcome. So, yes, Pedro de Azevedo Delo has one question.
Hi, Lucas. Thank you for the presentation. Congratulations. It was a really nice job, nice work that you have done. And you comment at the end that you could separate the hierarchical structure of the control and aware objectives. But I was interested to know, this is a very challenging topic and it's really interesting, but I was interested to know if you see that there is a separation in time scales of these objectives. Because
Yes.
if you treat the health aware problem slowly, you could lose some opportunity to enhance the health of the equipment. I don't know if I'm very clear. Could you comment?
No, you were. Yeah.
All right.
Yeah. Thanks for the question. And yeah, it basically depends on the problem. In this kind of problem, you can see that my time scale of degradation was in years. So yeah, you could actually separate in my case, or in this cases where is developed through years, but there are some more sensitive applications or systems, and in these cases you couldn't really separate the timescales. If you can separate the timescales, that's very nice. The optimization layer can give you yeah, the guidelines of how to operate your system. But if you cannot, then you would have to yeah, then you would have to treat everything at the same framework. And this would be a more interesting kind of problem to look into for the case of health aware control. But in this case, you have to set your objectives very very clearly, because let's say that degradation is of utmost importance for you, then you should have this as a directly controlled variable. You know what I mean? So maybe yeah, maybe it's an objective function that you're trying to optimize, and then you impose some constraints. And for this optimization function that you're trying to optimize, you could use some self-optimizing control, for instance. So there are some possibilities. But in our systems, it's easier to separate the timescales.
All right. Thank you.
Hi, thank you.
sorry, my mic was not open. So yes. So please, if you want to make some comment and question, you are very welcome. Maybe if I could ask, I don't know if André Souza would
Hello.
like to make some comments, because the process and was motivated by a process that was proposed by Petrobras, and so André was very much involved in the development of a model that was inspired by this process. I don't know if André would like to make some comments.
Yeah, I do.
Oh, thank you, André.
Hi, Lucas. First, congratulations for your work. I think that's very important to see such approach, mainly when the industry is focused on moving to digital approach and smart ones. So I think that's very good. Additionally, you implemented this approach in a very important process for Petrobras that we are developing, which is HISAP. So we are very interested in how many applications that the academic field can give to us or can collaborate with us. So I have maybe I have some questions for you, or something that you can bring your thoughts to us today. I'm mainly focused on field application. So my question or can be maybe, how do you see the confidence in the degradation models for real applications, and what kind of challenge or tools or preparation we from the industry will have to do to bring such approach into the field?
Thanks for the question. Also, yeah, I didn't mention during the presentation because it was getting a little bit repetitive, but the thermodynamic package that I used was based on André's implementation that just asked. So yeah, he's also co-author of our paper. So regarding how the industry should treat this kind of problem, I think there's a lot of opportunity in that, mainly because yeah, those degradation models are very flexible. So if you have data on them, it's very easy to fit anything, basically. So the main problem with these approaches, these degradation modeling approaches, is that you don't know a lot about the degradation of the system you're interested in. And it's very hard to know when you have no accurate models and you haven't had a lot of implementations. For instance, subsea applications, I mean, there are not so many, and the ones that there exist, I mean, it's what I mean is that's hard to have a lot of data on this kind of problem, and for you to have some synthetic data or try and reproduce the degradation patterns in lab scale or in pilot scale, it's a lot of investment to be done. So this could be a possibility to try and implement these systems in a more controlled environment in which we could aim for reproducibility, but also the development of more first principle models. I wouldn't believe that is a good approach, because as we saw, there's a very the randomness is intrinsic to the process. So I think it's best that we focus on statistical methods or machine learning methods, let's say, that treat this kind of random variables. So we aim for models that can describe how you trust on the data rather than only what is the health indicator of the system. So yeah, did I answer the question?
Yeah, I think so. Thank you.
Lucas, yes, are you listening? Okay. Well, I'm seeing here if there are any more questions. Okay, Lucas, I'd like to ask you something. You were talking about the generation of data in labs for this kind of degradation models. Are you aware, are you really, you see, participating in some experiments that are being developed at NTNU for these developments? You see some experimental. I think the person that is performing that is Matthias. Are you participating, or at least are you aware what he is doing, and could describe a little bit? José Matias.
Well, yeah, there is some. Yeah, I'm not involved in this work, but yeah, I know that Johannes Group is interested on doing experiments on this kind of system. But I'm not involved in the experiments. No, I'm more focused on the machine learning part now. I've left the degradation. Yeah, sadly.
Yes, I think Johannes is present now. Welcome, Johannes. I'd like to take the opportunity to ask our friends at NTNU if they have any comment, like Professor Skogestad and Johannes and Adrian or Dinesh. I don't want to force or push something, but do you have any comments? They are very welcome. Yes? No. Okay. So, Lucas, while we wait, if anyone else wants to make some question, I'd like to ask you something. Yes.
I think Johannes wants to talk. He's opened the micro. I think there is some connection problem, but maybe he wants to talk.
No,
yes, Johannes, we are listening. Yeah, if you want to talk.
I just wanted to say, if you're interested in going to the degradation part again, so we do are generating a lot of data, so it could also be interesting to see like what kind of machine learning methods you're using now, if they could be applied for this data that Jose is generating.
Okay. Yes. Thank you.
Nice.
Yeah. And Lucas, could you talk a little more about the use of particle filters, where they're very much CPU demanding? Do you see other forms of implementing them so that they could be more, you see, more accessible to use in real-time applications?
So I believe that for this kind of problems in which the processes are so complicated and so non-Gaussian, non-linear, that it's very hard to avoid particle filters. Of course, one can try and approximate the problem by unscented Kalman filters, for instance. That is a very valid line of research when developing this kind of model. But as for lowering the burden of computational effort, I mean, it's very well known that you can parallelize the particle filtering algorithm. And also, I mean, I think with today's computational capabilities, one could implement a like well-optimized particle filter algorithm. I'm not sure because I'm not implementing, but I think that this is a very close future. Let's put it that way. And
okay,
of course,
yes, I am kind of stimulating Ana Carolina to do that, you see, so that she could parallelize and try other, because she is also having some difficulties when she's applying, because the computational demand is very high in order for the sampling times that she needs to implement. Okay.
Yeah, I'm rooting for her. I'm in close contact with her. So
Okay, and yes, and maybe she is the one that may integrate all of these subjects that we are talking, because she said that she is going to try to be in contact with the, and maybe use the data that José Matias is producing. So it could be the person that will link everything. Okay, so I don't know if we do not have more comments. I'd like to ask if Ajimiro has something to tell. Wanna comment something about it?
Yeah, just to let Lucas know that his work is going forward. The Natalia Machado that was here, I think she left the meeting, and she will continue the Lucas work on that framework with 2 levels of optimization, separating the time scale and compare the approach and do something else. Okay, he's trying to improve the degradation model, but this is the most difficult part. Is how to build a good degradation model, as Lucas has mentioned. That's not an easy task. But anyways, this work is continuing, and so let's see the success of her. Okay, that's it.
Okay, so Lucas, I'd like to tell you that some people have written some compliments for your work. They liked it very much. And I would also like to announce our next seminar. It will not be next week, because next week will be a national holiday in Brazil. It's 7th September, it's the Independence Day in Brazil. But so in September 14th, we will have our next presentation that will be given by Julian David Hunt. Julian will present his presentation is entitled Next Steps for the Economy of Hydrogen. Julian is a chemical engineer by the University of Nottingham. He earned his diploma in 2008. He has also a Doctor of Sciences degree by the University of Oxford in 2013, and he is presently a visiting professor in the Mechanical Engineering program at Federal University of Rio Grande do Sul. I don't know if Marcelo Farenzena would like to add something else about it, or Jorge.
Mauricio, perfect.
Yes.
This is
Marcelo.
everything. Thank you very much.
Thank you. He is English, but I don't know if you from NTNU, you are invited already, so he can make the presentation in English, of course, and so you would be very, we would be very honored if you could be here again in our next presentation. So I'd like to thank you again, Lucas. Thank you very much for your very nice presentation. I think the students and the researchers from LADES and LADES at Copy and GIMSCOP at URGS have enjoyed it very much. And also people that from other universities. I saw that Professor Daci attended, and our guests from NTNU and Petrobras. Thank you very much. Thank you very much, everyone. So the session is now closed, and I don't know if Ajimiro wants to say anything else.
Well, thank you, Mauricio. Maybe Lucas makes some final comments.
Yes. I just want to thank you guys for the opportunity to present my work again. It was a very nice collaboration that we did. I learned a lot from you guys and with my colleagues at COPE. So it's very nice to be here presenting and repaying in a sense, and continuing this stream of research. This is research. So thank you guys.
I invited Professor Annie Barros, but she's not presently at NTNU anymore. She's now she's with Centrale Supelec. She's in touch with us, but she couldn't be here today. So thank you again very much. See you in our next seminar. Thank you.
See you
Bye
guys.
bye.
Bye bye.
Bye bye.